Let us try to now see for different carbon equivalent what is the behavior of the solid shell, whether there is bulging or there will be depression based on the solidification characteristics. Let us try to understand. So, let us first try to understand very low carbon equivalent chemistry corresponding to say 0.02 to 0.05% carbon equivalent. What happens in this temperature, in this chemistry range? As I have told you, solidification mode will be entirely delta. There is no question of gamma during solidification for this chemistry. So, solidification mode is entirely delta. So, solid shell, what is this solid shell? It is delta, it is thick, but this is weak. Why this is weak? Because the strength of delta is much low compared to the high temperature strength of gamma austenite. Delta ferrite has a high temperature strength which is 1/5 of the high temperature, relatively speaking, it is 1/5 of the high temperature strength of austenite. So, if you have total delta ferrite solidification for very low carbon, so what is happening? The solid shell is delta during and after solidification, slightly below solidification also is delta, and this delta is relatively thick because microsegregation is low. So, delta will also be relatively more in during solidification, but this is relatively weak because of the high temperature strength of delta ferrite is low. The mushy zone, I have told you, because microsegregation effect is less, mushy zone is narrow. This delta to gamma around solidus, there is no delta to gamma transformation around solidus, because delta to gamma will form only at lower temperature, that means after solidification, much after solidification. So, what is the consequence? Consequence is, because of this weak shell, though it is thick, but it is weak. So, this sticking tendency will be more. There is no delta to gamma around solidus, that means the bulging tendency or sticking tendency will be there, but depression tendency will not be there. That means shell shrinkage relatively will be less, because delta to gamma transformation is at much lower temperature and not in the crucial brittle temperature zone. So, what is happening? Sticking tendency is high, bulging tendency below the mold will be naturally high, sticking tendency, mold sticking tendency within the mold region will be high. So, for low carbon concentration, it is a sticking and bulging type of solidification behavior. Now, let us see what is happening for a carbon concentration, what we call the peritectic, that means around 0.1% carbon. I am telling it is around 0.1, but actually it is maybe 0.8 carbon to maybe 1.5, 1.6 carbon, 0.7 to say 1.7 carbon, carbon or carbon equivalent depending on whether you are talking of plain carbon steel or low alloy steel. So, this carbon concentration we call it a peritectic chemistry. So, what is happening? Initially solidification is delta, and its delta is available, that means delta is present till solid fraction around 0.75 or slightly lower than that. So, gamma it goes from delta to liquid plus delta to liquid plus delta plus gamma, that means the peritectic reaction is starting at a solid fraction of say 0.8, and the whole delta to gamma transformation, the peritectic transformation is taking place in the solid fraction of 0.8 to 1, which I have told 0.9 to 1 is the crucial brittle temperature zone. Solid fraction between 0.9 to 1 is the temperature zone, which is we call it a brittle temperature zone, because the ductility of the shell, solid shell, is 0 in this temperature zone. There is some strength in the shell, but the ductility is 0. So, when whatever strain is forming due to shrinkage of solidification or delta to gamma transformation, So, this is happening in the crucial brittle temperature region of 0.9 to 1. So, what is going to happen? You see here delta to gamma around solids is relatively high. Almost the entire delta to gamma takes place in this temperature region. So, the shrinkage is quite high. If the shrinkage is quite high, you have depression. So, this particular chemistry we have depression. So, we have a thick shell, and also at the end of the solidification, why at the end, even at say 0.75 or around 0.8 only austenite has started forming, and towards the end of solidification it is totally austenite. So, therefore, towards the end of the solidification the solid shell is very thick and strong. So, that means it can withstand sticking and bulging, but that is why the sticking and bulging tendency is not there at all, but it has the reverse, the other type of solidification characteristics. That means it will have depression because of high shrinkage. Shrinkage strain is quite high because this delta to gamma is taking place entirely in this brittle temperature region. So, very low carbon, it is sticking and bulging tendency. Around 0.1% carbon equivalent, I am telling around, it may be from 0.7 to 0.17. So, it is near the peritectic chemistry, we call it around 0.1, we will call it a peritectic so called. So, here the depression tendency is very high. Now, let us go to a carbon concentration above this, say 0.2 to 0.4. What is happening? Here delta initially is a delta transformation, still delta transformation will be there during solidification, which will be present till about 0.3% solid. So, that means around 0.3% of solid fraction delta is starting transformation to gamma due to peritectic reaction. So, in this carbon concentration initially there is delta formation, but delta to gamma transformation is taking place around solid fraction of 0.3 to 0.5. That means it is taking place above that brittle temperature region, which is 90% solid fraction to 100% solid fraction. It is taking place above that. So, delta to gamma around solidus is not there, it is taking place above that. Here around 0.1% carbon, it was maximum around the solidus temperature. For low carbon, it is lower than solidus temperature. At 0.1% carbon, it is near the solidus temperature. At 0.2 to 0.4, it is above the 0.9 to 0.1, that means much above the solidus temperature, around 30% to 50% solidus. So, here also delta to gamma is taking place higher than the solidus completion temperature. So, here also what is happening, because of microsegregation, because too much of delta is forming at the end of solidification. So, we have a thin solid shell, mushy zone is more quite big. So, the mushy zone is deep and the sticking and bulging tendency also relatively high. So, if we go to above 0.5% carbon equivalent, why above 0.5? This is the zone of peritectic concentration zone is about 0.5, 0.1 to 0.5. So, when you are taking a temperature which is above 0.5% carbon, so initially there is delta formation, not no delta formation, initially there is no delta formation, there is only austenite formation. So, here for more than 0.5% carbon or carbon equivalent, we have totally gamma or austenite solidification. Initially austenite is forming during solidification, and after solidification of course we have total austenite. So, here what is the solid shell? It is thin. Why? Because since solidification is through delta, as I have told you, the microsegregation effect for all allyl elements, particularly phosphorus, sulfur, will be more in the delta solidification, in the gamma solidification region, austenite solidification region. So, we have a thin solid shell, but it is relatively strong because it is austenite, whose strength at high temperature strength is more than that of delta ferrite. Here it was thick, but it was relatively weak. Here it is thin, but relatively strong, but it is thin due to microsegregation, a lot of microsegregation. So the marshy zone here is deep. Marshy zone for higher carbon, you see it is deep because of microsegregation. Here for low carbon it is quite narrow. So because the marshy zone is deep, this solid shell will be thin relatively. So what is happening here again, since this is thin, solid shell is thin, so it cannot withstand the ferrostatic pressure. The ferrostatic pressure will push it towards the mold. So it is again a mold sticking for high carbon, and when it comes out of the mold there is a bulging tendency. That means the two solid shell at the two ends of the near the the two surfaces of the mold, when it is coming out of the mold there is a tendency for bulging. The ferrostatic force will try to bulge it. So there is a relatively high bulging. So what is clear from this is that when we have a peritectic chemistry we have high depression tendency. When we have very low carbon we have a sticking and bulging tendency. When you have a high carbon, that means 0.2 and above, again we have a sticking and bulging tendency. The reason is different. Here we have a bulging or sticking tendency because of thin shell, thin solid shell. Thin solid shell is austenitic, but since it is thin it cannot resist the ferrostatic force, so it goes towards the mold and causes bulging when it comes out of the mold. But here there is not much of microsegregation, but it is delta, even after solidification for certain temperature it is delta, which has a relatively lower strength at high temperature compared to austenite. So the shell is weak, but it is shell is thick, but it is weak because it is delta, it is weak. So because it has low strength it cannot resist ferrostatic force or strain. So the question is, consequence is it will be sticking or bulging tendency. So only for the near the peritectic chemistry, that means chemistry near around 0.1% carbon equivalent, say 0.07 to 0.17 carbon, we have depression tendency. All other chemistry, whether it is low carbon or high carbon, we have a sticking or bulging tendency for different reason of course, but nevertheless the final effect is we have sticking and bulging for very low carbon and high carbon chemistries. Only around 0.1% carbon we have depression tendency. So now let us go to stainless steel. What I have talked is basically the plain carbon or the low alloy steels. I have told you around 0.1% carbon we have depression tendency. For very low carbon or very high carbon we have mold sticking and bulging tendency. When it comes out of the mold, then there will be bulging because of either soft shell or soft shell for very low carbon and thin shell for relatively thin shell for high carbon. So there is a sticking or bulging tendency for very low carbon and very high carbon. Only for around 0.1% carbon it is a depression tendency. The surface will have lot of depressions. Surface is not uniform. Surface is rough. We have a rough surface of the solid shell for 0.1%, around 0.1% carbon. Now let us see what happens for the stainless steel. I have told you, I have tried to explain when we are talking about the stainless steel, like how the solidification is taking place. I have explained. Yeah, let us see this. Here we are plotting the chemistry along nickel equivalent by chromium equivalent. I have told you that since it is stainless steel, there is lot of chromium, some of the nickel also. So normal iron carbon diagram or pseudo iron carbon diagram or carbon equivalent cannot explain the chemistry. Here the chemistry has to be explained through a ratio of nickel equivalent by chromium equivalent. Nickel equivalent is basically all elements clubbed together along with nickel, which is an austenite stabilizer, and all elements which are ferrite stabilizers have been clubbed together with chromium, which is again a ferrite stabilizer. So, chromium equivalent and nickel equivalent we find out from the base chemistry. So, then the ratio of this will determine how the solidification is taking place. Let us look at for 430, when the nickel equivalent by chromium equivalent is very low, solidification is through delta ferrite only. It is like very low % carbon. What happened for very low % carbon? Same thing is happening during solidification for ferritic grades like 430. Initially that is liquid and then liquid plus delta. Solidification is complete only through delta, and this delta to gamma transformation is taking place at quite low temperature. Depends on what is the nickel equivalent with chromium equivalent. It is very low, this gap is more. As we are going to higher and higher nickel equivalent by chromium equivalent, that means equivalent to higher and higher carbon equivalent for plain carbon or low alloy steels, this delta to gamma formation will be relatively enhanced at relatively high temperature. But what is important to remember is the solidification is totally through delta ferrite. Now, what is happening to say 301, which is austenite at room temperature, but high temperature what is happening? Let us see. Initially it is liquid, then solidification is through delta only, liquid plus delta. When the solidification is complete, then also we have delta. So, delta to gamma, this is the delta to gamma line. It is taking place below solidification completion. So, solidification is complete only through delta, and at slightly lower temperature to that, delta to gamma transformation is taking place in solid state. So, during solidification there is no delta to gamma formation. Now, I have put a rather dotted line here. What is this? Nickel equivalent, chromium equivalent, it is 0.55. Why I have put? Because you see this changeover between delta to gamma line and a solidification complete line. So, what is the implication? Implication is beyond, that means above 0.55 nickel equivalent and chromium equivalent, this delta to gamma transformation is taking place in during solidification, that is before the completion of solidification this has started. This is very important. So, in 304 what is happening? Just see 304, this initial delta, liquid to delta, then delta to gamma transformation takes place before the completion of solidification. So, delta to gamma is taking place around say 0.8% completion of solidification. When the solid fraction is about 0.8, delta to gamma has started transforming. So, again it is like around 0.1% carbon only. That means 304 delta to gamma transformation takes place towards the end of solidification. And what is the end of solidification? That region is the brittle temperature region. So, we have to be careful about this particular grade of stainless steel. Now, 316, where the nickel equivalent by chromium equivalent is more than say about, it is about 0.65 or so, 0.63 maybe. So, what is happening here? Initially again delta, but delta to gamma is taking place at much higher temperature. That means when the solid fraction is about 0.3 or so. So, delta to gamma has started forming, and most of the delta to gamma is over by the time we come to the end of solidification. So, there is a change between 301, 304 and 316. 301 delta to gamma is taking place after solidification is over. 304 delta to gamma is taking place towards the has started taking place toward the end of solidification. 316 delta to gamma has started taking place at much earlier stage of solidification. So there is some difference between 301, 304 and 316. Now let us come to a chemistry which is above this 0.74, which is equivalent to 0.5%, 0.5% of carbon equivalent, which I had mentioned. Beyond this, that means when nickel equivalent by chromium equivalent is above 0.74, what is happening? The solidification is through austenitic mode only. There is no delta formation at any stage. So solidification is through austenite, and when it is completed, then also it is solid austenite. So 310, again one popular stainless steel grade. Here, because the nickel equivalent by chromium equivalent, which is around 0.8, is more than 0.74, this dotted line. So this transformation is taking place, sequence of solidification is through austenitic mode only, there is no delta. So if we understand these solidification modes for the different stainless steel chemistries, I have mentioned for 430 it is totally ferritic, and austenite formation is much lower temperature. 301 again it is ferritic solidification, austenite solidification starts below solidus temperature. When solidification is complete, after that only delta to gamma is taking place, that means that transformation is in solid state, not in the liquid state. 304 delta to gamma transformation has started towards the end of the solidification. So this is a very crucial chemistry which is very vulnerable to the delta to gamma transformation takes place during the end of the solidification. So this is a risky chemistry, we have to be careful on that. So 316, that risk is there, but relatively less, because this delta to gamma is taking place, has started taking place at much higher stage of solidification. 310s total austenitic solidification, there is no delta to gamma, only gamma solidification. So the difference in solidification mode I have tried to explain from this different for the different chemistries. Now let us try to see how does it the solidification is taking place and what are the implications on the sticking or bulging tendency, which I have told is very important. This bulging or depression behavior based on solidification characteristics for stainless steel. So 430, I have told you the solidification mode is entirely delta. Solidification is taking place through ferrite only. So this is one important observation. For 301, again it is delta. So this delta to gamma around solidarity is much less. It was slightly lower than solidus. So it is very minor. It is almost 0. Here it is 0. It is almost 0. 304. This delta to gamma. You see, delta is present till around 0.75, and delta to gamma for 304 is taking place mostly in this temperature region. So towards the end of solidification, you have lot of delta to gamma transformation taking place. 316, as I told you, delta is present, initially delta and is present only up to 30% of solid fraction. Above that we have gamma transformation, and delta to gamma is taking place above this crucial temperature, brittle temperature region between corresponding to 90% and 100% solidus. So this 316 delta to gamma is taking place not around solidus, it is above solidus before the completion of solidification. 310s, of course, as I have told you, is the entirely austenitic solidification. Therefore, there is no question of delta to gamma transformation at all at any temperature. Now, what is happening to the solid shell? Like very low carbon, as I have told you, here also for this ferrity grade 430, that means nickel equivalent chromium equivalent is very low. Entire is entirely through delta, and delta to gamma takes place at much lower temperature. So, in solid state the solid shell is therefore thick because microsegregation is quite low, but it is weak. Why it is weak? Because it is delta ferrite, whose high temperature strength is relatively low compared to that of austenite. So, like very low carbon, this 430 ferritic grade is also the solid shell is thick but weak during solidification, and the mushy zone is relatively thin. But since the solid shell is weak, it is difficult for it to withstand the ferrostatic pressure, and the shrinkage is also less. So, therefore, this sticking and bulging tendency will be relatively more, depression tendency is not at all there. So, because of the weak shell, solid shell, which is delta, even after solidification it is delta for quite some time, for quite a temperature, lower temperature delta is stable. So, the delta to gamma transformation takes place at much lower temperature. So, for quite a big range of temperature we are having a weak solid shell because it is delta ferrite. So, because of this there is a tendency for mold sticking within solid or within mold, and below the mold there is a tendency for bulging. So, because it is soft, the solid shell has low strength at high temperature. So, bulging tendency high. So, therefore, we have to be careful about that, because whatever strain will be there at different temperatures, there is a possibility of causing crack at the interior of the solid shell. So, we have to be careful about that. 301 entirely delta, solid shell is thick, but it is not very weak because towards the end of that, just after the solidification, it is transforming to austenite. So, austenite high temperature strength is relatively high. So, I have not mentioned it is thick, it is not weak, it is thick, but it is relatively strong. So, mushy zone here is again relatively thin during solidification because the solidification is entirely through delta ferrite. So, therefore, the chances of microsegregation, incidence of microsegregation is relatively less. So, mushy zone is thin, solid shell is thick. So, here also the tendency of mold sticking and bulging is not there, but there is a minor depression almost very, because of the delta to gamma towards the end of the solidification slightly lower than that, it is almost negligible. Here there was no depression at all, here it is very minor. But 304 is like our 0.1% carbon steel. What is happening? You see, delta is present still about 0.75% of 0.75 solid fraction, that means 75% of solid is there. Only below that, that means gamma is started taking place around 0.8 to 1% solid fraction. So, what is happening here? 0.9 to 1, as I have told you, is the crucial zone of brittleness, temperature zone. So, therefore, this particular grade will have a tendency to form crack near the solidus completion, because delta to gamma around this is very high, delta to gamma is very high. So, these will have implication on the solidification characteristics and crack formation. Here also mushy zone, because initial solidification is to delta, so relatively thin, but here depression tendency is very high because delta to gamma is taking place in the crucial brittle temperature region. So, depression tendency is high, and no, there is no mold sticking or bulging. Depression tendency high means surface will have lot of depression, it is uneven surface. If you have uneven surface, because of that heat transfer gets affected. So, the grain size of the dendrite, they become relatively thicker compared to other chemistries. So, depression will have many implications on quality. So, 304 is like 0.1% carbon, we have rough surface, we have depression, we have coarse grain. I will come to it later on. 316, what is happening? Delta is present only up to 30% of solid fraction. Lower than that, gamma has started forming, and gamma will be complete before the crucial brittle temperature region. Therefore, the relative amount of depression is there, but it is less compared to 304. The delta to gamma around solidus is moderate, that is why depression also will be moderate. Massy zone is also moderate. Here it was thin, but it was slightly increasing in thickness. Why? Because the gamma transformation is taking place in the solid state during solidification at relatively higher solid fraction. So, solid shell is moderate in both respects, from the thickness point of view, from the strength point of view. 310S, as I have told you, it is the solidification is entirely through austenite, and if it is entirely through austenite, you have lot of microsegregation. So, the solid shell is thin but strong because it is austenite, whose high temperature strength is relatively more. But because it is thin, and I have told you the thickness, if it is thin, the strain is inversely proportional to the square of the thickness. So, if the thin shell, it cannot withstand, even it is slightly strong, it cannot withstand the ferrostatic force. So, the sticking strain and bulging strain will be quite high. So, the tendency is it will have mold sticking tendency, it will have bulging tendency, depression is almost not there at all. So, if you try to understand what are the solidification behavior, and consequent to that whether there will be bulging, whether there will be depression, what chemistry will have depression, what chemistry will have bulging. So, I have mentioned that for plain carbon and low alloy steels, the chemistry around 0.1% carbon or carbon equivalent, it has depression. Very low carbon and very high carbon, they have sticking and bulging tendency. The behavior is similar for stainless steel, but of course, here carbon is of no consequence. Here the nickel equivalent by chromium equivalent is representing the chemistry. So, 304, but the nickel equivalent by chromium equivalent is around 0.55, 0.56. Here it has lot of depression tendency. For low nickel equivalent by chromium equivalent, for 430 and 301, depression is not there, only sticking and bulging. Similarly, for high carbon, or rather not high carbon, high nickel equivalent by chromium equivalent, that means when the solidification is only through delta, only through rather austenite, we have high tendency of mold sticking and bulging. Depression is not there at all. Here the massy zone will be thick during solidification, and we have a very thin solid shell during solidification, which cannot resist the ferrostatic force or strain. So, the bulging strain, sticking strain is more, that is why you have mold sticking and bulging tendency. Thank you very much.